Hi everyone, I'm Jiao Zhang from UC Riverside, and today I'm going to present our work BP-NTT, which is in collaboration with UCRI. Lattice-based cryptography is a promising technique to protect privacy and data security in the next generation of computing and communication technologies. The most important and time-consuming kernel within common lattice-based cryptography applications is polynomial multiplication. From the schoolbook, the computing complexity of polynomial multiplication is n squared, which includes n squared multiplications. In implementation, number theoretic transform or NTT is always adopted to reduce the computation from n squared to n log n. For example, polynomial A and polynomial B will first be transferred into entity domain and then perform dot multiplication and then perform inverse NTT to get the result. However, even with the help of NTT, the polynomial multiplication still costs the most execution time. From profiling on two post-quantum algorithms, Kyber and dilithium, there is still 32% to 50% of execution time spent on NTT or inverse NTT. Actually, NTT acceleration is not that easy to implement on hardware. In the figure, we show a common algorithm to implement NTT, which is called Kuretake butterfly. We can see that among three stages in this process, each stage has different and complicated data dependencies. In addition, each multiplication within the NTT is appended by a division-based modular operation, which is unfriendly for the hardware. There are some existing ASIC solutions, for example, Layer, Sapphire, trying to tackle this NTT acceleration problem. However, they suffer from the problems such as low such efficiency due to frequent data movement and limited flexibility due to the fixed modular multiplier or data or control path. Thus, the problem becomes how to achieve efficient and flexible NTT acceleration. To achieve these issues, memory-centric solutions are proposed, such as recruiter and duality cache, or etc. They show potential high efficiency and high flexibility due to reduced data movement and general vector processing units. However, there are still two challenges to accelerate NTT with such computing memory technique to render high efficiency and flexibility. The first challenge is that existing data layout for computing memory incurs redundant shifts. Thus, we propose a shift-optimized data alignment to avoid redundant shifts. Another challenge is that bit-parallel modular multiplication induces unnecessary carry propagations. To avoid such unnecessary operations, we propose carry-safe modular multiplication. The details will be discussed later. We call our proposed design BP-NTT. It repurposes the last level cache to perform bitline computing, which brings great security measures and high throughput to our design. BP-NTT also uses shift-optimized data alignment to reduce latency and energy consumption. And last, we employ bit-parallel modular multiplication to reduce latency and error overhead. Then we will talk each part one by one. BP-NTT repurposes last level cache to perform bitline computing, thus no plaintext will be exposed outside the chip, which does not expand trusted execution environment, which means it brings high security. Each BP-NTT bank has 3 data subarray for computing and 1 subarray for control. With this control scheme, the control commands can be generated offline. Thus, there is no runtime overhead for CPU. Each data subarray is repurposed to be able to perform bitline computing, which has high parallelism. 2 decoders and modified sensor amplifiers are introduced. Compared to prior works, BP-NTT adds 2 muxes and one latch to support 1-bit shift. The total error overhead is within 2% in a 256 times 256 subarray, which is trivial. Now, let's focus on the shift-optimized data alignment. From our profiling, we found that about 50% operations in NTT are shifting in bit serial data alignment. In addition, such shifting destroys the parallelism brought by the bitline computing due to the bit-by-bit shift fashion. Let's take an example. To achieve NTT, first, trivial factors are multiplied with the polynomial coefficient, and then the results are left shifted to align with the corresponding coefficient. Then they perform addition and subtraction, and finally, right-shifted and return back. This is the computation for one stage. However, step 2 and step 4 are redundant and destroys the parallel computing. To avoid these redundant shifts, we propose shift-optimized data alignment, which only reserve necessary modular multiplication, addition, and subtraction. Thus, it brings 4-step stage into 2-step. By placing coefficient per row, the data alignment can be implicitly achieved by selecting corresponding row with its index. Thus, there's no shift operations required to align data. In addition, this data layout also enables our proposed bit parallel multiplication, which reduces latency and error overhead. Next, let's focus on bit parallel modular multiplication. Traditionally, compute in memory is not good at a bit parallel multiplication since carry propagation ruins the parallelism. For example, the carry propagation-based multiplication has n-square computing complexity, while a carry propagation-based addition has n computing complexity. In addition, carry propagation-based multiplication requires extra columns for overflow bits, which lowers the parallelism. For example, for the 4-bit input, 8 bits are necessary to store results, even though this 8-bit result will be modularized into 4-bit result afterwards. To avoid unnecessary carry propagation, we propose a carry-safe-based bit parallel modular multiplication algorithm. The main contribution is that we reduce the addition complexity from n to constant by using the carry-safe concept. In addition, only 4 bits are required to store inputs and results, thus high parallelism is maintained. Please check our paper for details. In general, high security and flexibility is brought by on-chip design and compute-in-memory technology. And high throughput and low overhead is resulted from shift-optimized data alignment and bit-by computing. The low latency is from our proposed bit parallel modular multiplication. In general, a high-performance, low-overhead, energy-efficient, and flexible NTT engine can be achieved. We evaluate our proposed BP-NTT and baselines with PyMTL3, OpenRAM, Synopsys Design Compiler, Cadence Innovus, and Destiny Simulator. We compare BP-NTT with other designs. Note that all the results are normalized to BP-NTT. First, compared to ASIC design, Sapphire, it shows that Sapphire has low throughput and limited flexibility. When compared to in-RAM designs, both of them shows low energy efficiency, while CryptoPIM has extra limited flexibility due to fixed interconnection between arrays. Compared to in-SRAM design, MENTT shows high error overhead and low energy efficiency. We also conducted flexibility analysis on BP-NTT. With the increasing bit width, parallelism decreases due to the fixed array size. With the increasing polynomial order, the latency and energy increases more rapidly because extra shift overhead is introduced to handle large polynomial order. In conclusion, BP-NTT repurposes last level cache to perform bitline computing, which brings high security and throughput to our design. BP-NTT also uses shift-optimized data alignment to reduce latency and energy consumption. And last, we employ bit parallel modular multiplication to reduce latency and area overhead. According to our evaluation results, BP-NTT can achieve up to 138 throughput per power than state-of-the-art with minimal area. Glad to be here. Thanks.